Okay, so welcome back to particle physics and the standard model. This is lecture 11, and last time we had started looking at what really Feynman diagrams were. We learned that they are pictorial representations of the quantum amplitude, and in particular the transition amplitude from an in state to an out state, correct? They are not representations of particles actually colliding or annihilating in time and then traveling along and splitting and so on. Everything in a Feynman diagram happens in one point in space and time, and that it's all happening in momentum space, because this is a way to calculate amplitudes. All right. So we saw some basic things about Feynman diagrams, about interaction vertices and so on. So in this class we'll explore that some more before we move on to spin and spin statistics theorem and so on. All right, very good. So last time we ended by saying that you have tree diagrams, right, and you had any number of loop diagrams. So this time I am going to skip the arrows. All right, you should learn how to draw the arrows. I can have a bubble like diagram on the mediating gauge boson. I can have a loop on one of the external legs representing the in state fermion and so on, right. And we saw that we have to add up all these terms to get the actual complete amplitude, but then we do not really have to in many cases, because in the amplitude every vertex comes with a coupling constant, and so if you do a perturbative expansion of the amplitude, you will find that the tree diagrams usually contain much fewer vertices, so much fewer coupling constants, and hence those terms would dominate over the loop diagrams. Okay, trees dominate over loops usually. There is always exceptions, right. So let us look at one of the exceptions here. Okay. Now pause your video and think about this for a second. How do you think exactly the pion decays to 2 photons? What do you think is the Feynman diagram for this? In other words, what are the interaction vertices using which I could draw this, knowing the the fundamental forces that you know about. All right. So think about it, and one tip I am going to give you is, as you follow along this lecture, read Griffith's chapter 2 on the side. Okay, Griffiths talks about a lot of these. He does not give you all the subtleties about amplitudes and so on, but read it side by side, and while you are doing it, try to answer this question: what diagram can I draw to have pi 0 decaying to 2 photons? Okay. A simple diagram that one could think of course, would be a pion is UU bar plus DD bar, right. So I am just going to take the UU bar part of it without loss of generality. I have UU bar, I exchange another U over here, and I have 2 photons, because this vertex is allowed, correct. UU gamma perfectly allowed. So this diagram is perfectly fine, right. But I can think of yet another somewhat crazy looking diagram which looks like the following. Now in this case I am going to just take the pion itself as a scalar field. Okay, it is totally possible, it depends on what you want to do with the amplitude. The pion is a scalar field, it contains UU bar. I am just going to draw the scalar field. All right. So just to be clear, this is also the pion, this is also the pion. Okay, it depends on exactly what you want to do with the pion, how you draw it. All right. And then I am going to draw a triangle diagram like this, which is a loop. Okay, and in this loop I can have all the charged quarks I want. Okay, so I can have U, C, T, down, strange, bottom, the electron, muon, tauon, and so on. All the fermions that have charge that I can think of. Okay, any, by all I mean, you know, I can draw many diagrams. In each diagram I can have one single charged fermion, electrically charged fermion. Again, in that case I can draw two photons coming out of pions, the pion, right. Now this is a loop diagram and that is a tree diagram, right. Now which one do you think wins, which is dominant? It turns out that this is the dominant one and this is the, well, subdominant one. Okay, this is one of the famous exceptions where a loop diagram is more dominant than the subdominant. In fact, this is dominant by far. Okay, actually, no expert thinks of this diagram, thinks of the tree diagram when thinking of pion decay. That's because sometimes you have things called anomalies in the theory. In this case, it's a chiral anomaly that makes this diagram possible, so we're not going to really talk about anomalies right now. We may take it up later in the course, but it's the anomalies that actually make some loop diagrams larger than their tree diagram counterparts. Okay, so this just illustrates there are exceptions to this rule. Okay, just keep that in mind. Okay, so you saw me draw a composite particle like a pion, either as the resolved UU bar or as the scalar itself, right. So in general, how would you draw composites? In general, if I want beta decay, for instance, if I want to depict a neutron going to proton, electron, antineutrino, right, beta decay. How would I draw it? Well, there is a couple of ways again. I can either draw the neutron itself, okay, as a fermion state, and then it goes to a proton in the final state. Let me redraw this slightly, okay. So, and then no, this is fine, I think this is fine. So, it goes to a proton in the final state by emitting a W boson, and the W in turn goes to an electron and antineutrino. Okay, this is a perfectly valid way to draw this. All right, and in this case, this happens to be a W minus because the way I have drawn it, time is flowing to the right. Right. Remember, time is not like real time. This is just to distinguish between the in state and the out state. All right, this we talked about last lecture. But if I want to really see what is going on the inside of a proton and the inside of a neutron, what really is the fundamental state that is changing, that is transforming under beta decay, I can draw the same diagram, I can draw the same process in the following way also. Okay. So, what is a neutron after all? It is DDU, right. So, let me write a U D D, that is the neutron, and then I am going to make one of the U's just go along for a ride, and then I have the D also go along for a ride. Now, to convert this to a proton, I am going to turn the D quark into a U quark, correct. This is the proton, right. Okay. And what has happened now, the D has flipped to a U. So, I know that this vertex exists, a UDW. If you do not believe me, go look at Griffiths again. Griffiths tells you all the vertices allowed in all the fundamental forces, right. So, for the weak force W is the mediator. So, I have a W, again it is a W minus, and that is the one that I am going to split into an electron and an electron antineutrino. Okay. So, this is how you draw what is happening on the inside as well, alright. Similarly, if I want to represent a charged pion going to an anti-muon and a muon neutrino, remember we saw this when talking about parity violation, CP violation, etc., right. How would I depict this in a Feynman diagram? Especially if I want to represent the components of the pion composite, again very simple. I know that a charged pion is a UD bar I draw these arrows and this is the vertex that I have, that is the vertex given to me, and that is the one that goes to mu plus and neutrino, alright, and so on and so forth. Okay, good. Now, we talked about a little bit about these arrows that I have been drawing on the fermion lines, correct. So, these arrows roughly represent, if I were to draw an arrow in the direction of time, that generally represents the fermion, and then if I were to draw an arrow in the opposite direction to time, that generally refers to an anti-fermion. Okay. So, you can see this pattern again and again all over the place, right. Although, so here, so as you can see here I have made a little mistake. So, the fermion is in this direction, the anti-fermion is in this direction. Okay. Now, I am going to tell you not to take this rule very seriously. Okay. I do not think Griffiths really says this, you will not find this in many textbooks, but take it from me, do not take this rule too seriously. Okay. There is a way in which you can flip the convention, the fermion could have the arrow in the opposite direction to time and the antifermion could have an arrow in the forward direction in time, and there is a consistent way to write down the Feynman amplitude. Never forget that these rules are arbitrary, that serve to in the end write down the expression for the amplitude by looking at a diagram. That is the most important thing here. Okay, the quantum amplitude is the most important thing here, not all these little rules about which way time is, which way the arrow is and all that. Okay, you can do whatever you want in a Feynman diagram as long as you write down your own set of consistent rules. You can write down your own Feynman rules if you want. Okay, never forget that. So, let me illustrate this with some dramatic examples. Okay, about what about the uselessness of these arrows. Okay, well, not the uselessness, about the non-rigidity of the conventions used in how you draw the arrows on fermion lines. All right. Let us take one example, one kind of a famous example. It is called neutrinoless double beta decay. This is a process that has not yet been observed in experiment, and experimentalists are working very hard to try to look at this experiment, to see this process. Okay, it is represented as 0 nu beta beta. So, neutrinoless double beta decay. Why is this important? Because if you were to see this, then it would prove, let me probably change color, prove that neutrinos are Majorana and not Dirac. In other words, loosely speaking, it would show that neutrinos are their own antiparticles. Okay. How is that? The best way to see this is to draw the Feynman diagram. So we just saw how beta decay actually proceeds, right? We just saw over here that this is the heart of beta decay. The D turns into a U emitting exchanging a W and emitting an electron and antineutrino, correct? So why don't we start just with the D? I am not going to bother about where the D quark is sitting in, it is sitting in some neutron or whatever. I am just going to start with at the quark level, okay. So here is the D quark turning into a U quark. So I am going to draw one beta decay first, okay. That is a W, and what happens? You emit in an antineutrino and an electron, okay. I am going to draw another beta decay, that is why it is a double beta decay, okay. Two neutrons sitting in some specially prepared nucleus are decaying in this case. So the D quark in that one also converts to a U quark, another W is exchanged, another electron is emitted. Now look what happens. Here is another anti-neutrino, so I am going to draw the arrow in this direction, okay. Notice what has happened on this fermion line. Let me draw that line again for you in slightly bigger over here. This line, okay, is I have drawn, there was an anti-neutrino here and an anti-neutrino here. So what has happened, right? This line now contains two arrows. Not only that, those arrows are pointing in the opposite direction, correct? So when that happens, so that X is not a wrong, that X denotes what is called clashing arrows. What to do if you have clashing arrows? Nothing, it is absolutely fine to have clashing arrows. There is an absolutely consistent way to interpret this diagram also into an amplitude. It just shows in this case that like there is no fermion number involved here, that the antineutrino and the neutrino are one and the same thing, okay. That is what it ultimately indicates, okay. So that is perfectly fine. Let me give you another example of clashing arrows. Maybe this time you will see how the clashing literally happens, okay. Now imagine, okay, this is not happening in the standard model. Imagine that there is a fermion that has 0 electric charge. In fact, it is charged 0 under everything, okay. So I am going to call it a singlet, that is the technical term. It is a singlet of the standard model. It is just charged, it just does not participate in any of the fundamental forces of the standard model, okay. And then imagine I introduced another particle, I am going to call it E with a tilde on top, you will see why, alright. This E tilde has -1 electric charge, or the total, the electric charge is, the absolute value of the electric charge is 1, let us just say, let us just put it that way, okay. So electric charge, and otherwise that is it actually, and also that it is a spin 0 particle, okay. In other words, it is a spin 0 particle, but in every other respect it behaves like an electron, that is why I put an E tilde, alright. Suppose I had these particles, then by conservation of charge, do you agree that I can always draw a vertex like this, an electron, a chi, and an E tilde. Do you agree with this? The charge of the electron is eaten up by the charge of the E tilde, and then the chi is, because the chi is electrically neutral, and electron is a spin half particle, but the chi is also a spin half particle, right? We just said it's a fermion. So the spin is taken away. So I can attach either a spin 0 or a spin 1 to this vertex, and that is what I have done. I have attached a spin 0 particle, correct. So this vertex is always allowed, which means I can draw this scattering process. I believe it is called Baba scattering or Mott scattering. I think it is Baba scattering, okay, via this vertex, right. So E tilde chi. I can draw yet another diagram for this, right. So usually I have a gamma or a Z boson. Let me just draw it, okay. So generally I would have the E minus E plus. I am not going to draw the arrows now. I can also have E minus, E plus, exchanging the photon in this direction, correct. If I have a photon, I can also have a Z boson. So this is what I would usually have, but now we are going to draw more diagrams using this new hypothetical vertex that I just introduced. Alright, what can I do? How can I get E plus E minus going to E plus E minus with this vertex? Maybe you should pause the video to try to draw this yourself, okay. The hint is you have to use some sort of a loop to get this, alright. So it is a good practice to start using vertices. It is like Lego blocks, right. You have to fit them and try to get the process that you want, alright. So try this on your own and then come back to the video. You will find that this is one possibility for a loop diagram. So I am going to draw starting with an E minus. I am going to use the vertex to get an E tilde, okay. So what happens? We just saw the vertex here, right. So it turns into a chi, and then I am going to insert one more E tilde. So the chi turns back into an electron, and then what do I have down here? Quite simply E plus and E plus in the in and out states, and in between the E plus has turned into a chi, right. Okay. Now that I have drawn this, here is another question. Is this the only diagram I can draw with a loop or something else? So in the previous lecture I asked something very similar, right. And the answer is you have to fix the momentum labels, and then you can swap the lines any which way as long as the in and the out states are the same, correct. The total in state and the total out state are the same, right. So following that rule, I can always draw one more diagram with the same vertices where I start with E minus and an E plus. Once again I exchange an E tilde, but look what I am going to do now. I am going to take the internal chi down here, okay, and finish it with an E plus. Similarly, I have an E minus in the final state, right. Once again I exchange an E tilde here, and I am going to take the internal chi, I am going to join up these 2 points now, this and this, and just for illustration I am going to show it like this, that this fermion is is distinct, it looks like it is crossing, but it is distinct from the other line, alright. Now how should I draw this? Look at the fermion arrow here, it goes to the right here, right. The fermion arrow for the electron goes to the right, correct. Okay. So, as I come down, I have to draw the arrow again in this direction, because that's the direction in which the fermion line was going anyway, right. Then what happens to the fermion line over here? It's been going like this. So, I have an arrow here. See what has happened now. These two arrows are literally clashing now, correct? That's not all. Look at this arrow. This fermion flow is going in this direction. So, I would draw an arrow like this here, and then this arrow is going in this direction, right. So, I would draw another arrow over here. So, once again that is a clashing arrow. In this case, it's more like a tug of war arrow, right. Those two arrows are pulling each other apart, but it is also called a clashing arrow, right. So, the broad moral of all this is that ultimately many weird things can happen within Feynman diagrams. There is no rigid set of rules as such, okay. It is a bit like chess, right. So, there sometimes you keep playing rigidly, and then at the end of the day you will do some castling, which looks completely counterintuitive, right. That is very much how it is. The point here is to write down a mostly self-consistent set of rules to depict the transition amplitude, okay. That is the whole point of Feynman diagrams. Just keep that in mind. We will not be using Feynman diagrams too heavily in the course, but often I will be drawing these diagrams, and you should have some sense of what are the processes I am depicting, what is going on behind the diagram, and so on, okay. So, again I highly recommend going through Griffith's chapter 2 for this, okay. So, that is all I wanted to say about Feynman diagrams. So, in the last few minutes, let us start a bit on, let me just refresh your memory on things that you know in quantum mechanics, and then in the next lecture we will take that up further, okay. So, this has to do with spin, angular momentum, and so on, okay. So, said differently, we are going to start our module on continuous symmetries, okay. This is where the course is going to start moving towards the standard model, alright. The world is described by and large using continuous symmetries, okay. So, think of this as a warm up involving quantum mechanics that you are already familiar with, right. So, let us start with notions of angular momentum and spin. Okay. So, I am just going to write down a few equations that you all should already know, right. Quantum mechanics is a prerequisite for this course, but this is just to jog your memory, right. So, using the usual notation for angular momentum operators, orbital angular momentum, what is this? What is the commutator of Lx and Ly operators? It is IH bar Lz, correct? It is not 0, that is the most important thing. That is the most important thing. The second important thing is that non-zero quantity is the Lz operator with an I in front, and of course, there is always an H bar in all these, right. That is the measure of quantum physics, H bar. So, I am not going to write all the 3 permutations, I am just going to say and the cyclic permutations, correct. So, what else, what other commutation relation do we know involving angular momentum? We know that if you took L squared right? What is L squared? L squared is just nothing but L dot L, right? So, the commutator of L square with one of the components without loss of generality, hence I am writing for all three components. What is this? This of course is 0, correct? So, what is the implication of this? What is the physical implication? It means you can't measure all three components, right, of the angular momentum simultaneously. Correct? Only the total L squared and any one component. That is why the commutator of L square with any component is 0, but the commutator of any two components is non-zero, right? And this any one component conventionally is taken as Lz. Okay, so we usually talk about L squared and Lz, Lz. Good. All right. So, let me finish up with one last thing. What are the eigenvalues of L square? Again, this is something that you know already. It is an integer L times L plus 1. And what are the values taken by L? Well, I just said it. These are whole numbers, right? 1, 2 and so on. Those are the values of L square that you can measure, right? So, in the same vein, what are the eigenvalues of Lz? There are many, and we usually write them as m with an L subscript to remind us that L is involved somehow in this, right? So, what does it mean? That means ml can take values of minus L plus 1 and so on. It will take 0, L minus 1 L. What does this mean? It means there are 2 L plus 1 values for ml. That is exactly why you have 0 in the, it is an odd number, right. So, you have 0 as one of the values that you can measure as Lz, which is kind of obvious if you think about it, right. The z component can be 0, there is no reason for it not to be. Okay. So, now that we have refreshed on a bit of angular momentum, we will apply this concept to spin in the next class and take up spin statistics theorem and so on. Alright. So, alright, I will wrap up here, see you in next class. Thanks.